Hey guys, today we are on student activity sheet 2 of topic 2, which is multiple representations in the real world. And we are in the exploring tiling square pools section. Okay, so just a little bit of background here. We have Anthony, who, if you guys remember from the other day, was helping his dad, Mr. Chen, with his pool company. Okay, so if you remember, this is what our pool looked like. He had a 1 yard pool, 1 yard square pool. And like we said the other day, 1 yard is equivalent to 1 foot. So within the 1 yard, we had 1, 2, 3 feet on each side. Okay. And then we also had the 1 foot tiles that went all around the border. So with this, I want you guys to think about what it would look like if Anthony made pools that were just a little bit smaller. Okay, he decides that he thinks that he can come up with a plan so that he doesn't have to necessarily draw it out each time. But before he comes up with this plan, let's think about what these pools may look like. If my screen would load here, here we go. Okay, so he gets to work. Again, here's Anthony's 3-foot pool square and the border. Okay, so what I want you guys to think about is if he made a pool maybe 1 foot smaller, what would it look like? So I'm going to take my tiles, and instead of having a 3x3 pool, we're going to just have a 2x2 foot pool. Okay, and what if we went even smaller than that? How big would his pool actually be? That would be 1 foot. Okay, so I want you guys to go ahead and take a moment to get those pictures of our 2 pools drawn on your paper over here. Okay, so hopefully you guys have your pools drawn now. So again, this is what if it was just a one foot pool, if it was a 2-foot pool, and then we have the 3-foot pool over here. But we need to put the tiles around them too. So let's see how we would go ahead and plan this out. Okay, we know that for his 3x3, he had all the tiles on the sides. Boop, 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 boop. Okay, but then he also had 4 tiles in the corners. So we're going to say 1, 2, 3, and 4. Okay, I want you guys to pause the video for a second, and I want you guys to draw what the tiles would look like around our smallest shape and around our biggest shape, and then unpause to see what we get. So hopefully your guys' answer should look a little bit like mine. When he draws those pools, when he goes ahead and fills in the tile, we end up with all of them filled in, including the 4 corners on each of them. So let's look at how much are in each side of those. Okay, if you look over at his single pool length, we've got our 4. Whoops, that one's supposed to be right there, and then our 4 corners. So with that, when it is 1 foot long, there's going to be the 4 sides plus the 4 corners to give me 8 tiles in the border. Okay. When we have 2, 2, 2, and 2, and you can count them over on my picture that we've drawn also, we end up with 2 tiles per each of the 4 sides, which is 8, plus the 4 corners, to give us 12. So when we have a 2-foot side pool, we have 12 tiles in the border. Okay, and then lastly, if it's going at this pattern, if we have 3-foot sides, 3 times the 4 sides is 12, plus our 4 corners, that would give us 16 total tiles. But we've found that information already. Okay, let's go ahead and flip to the back side of that page. And I'm going to switch pages here. Maybe. Okay, so again, we have our pictures that we had drawn here and we had our table. I want you guys to think about, what does this numerical representation of the problem reveal? As a reminder, right here was our concrete representation. Our table is our numerical representation. What does this table reveal about the problem? And then how does it actually connect to this model that we have? Well, something that I noticed was that each additional foot of the pool adds 4 tiles. Every time we added a foot on, we added 4 tiles over here. Okay, so I'm going to write that down. Each foot added on equaled 4 more tiles. Okay, let's see if we're right here. Yep. So something else I do want to note is that the number, and I'm going to shorthand this, the number of tiles in the border is the length of the side of the pool times 4 plus 4 tiles on the corners. Okay, so if I took what I just said right here and I wanted to put this into a symbolic representation, and our symbolic is an equation. When they say function rule, again, that function rule, guys, that is a fancy schmancy way of them saying equation. Okay, write that down if you need to. What that means is equation. And there could have been a number of different ways we came up with this. The most basic one being that our total number of tiles, T, equals 4 times the length of the side of the pool plus my 4 corners. Okay, some other equations that mean the same exact thing, but maybe they make better sense to you, is our total number of tiles equals 4 times the side of the pool plus 1. Okay, another way you could think about it is my total number of tiles is 2 times all the sides plus 2, the length of the side plus 2, plus 2 times the sides. Okay, that's a whole lot right there. My mind sees just this purple one the best. You may see one of these ones better, but this top one makes the most sense to me. I'm going to put a little smiley face by that one. That's the one that we like, okay? All right, going on to question number 5. I want you guys to circle this one. We're going to come back to this one in class and then possibly some homework. Okay, so we're going to skip page 5, the front and back of it, and we're going to start our next thing on page 6 here. Man, my Agile Minds is going extremely slow today. We're going to jump over to page 8 on Agile Minds. Okay, so with this, guys, we had the information that they have on the length. These are the same tables that we just had down. 1 foot of pool gave us 8 tiles, 2 feet of pool, 12 tiles, 3 feet of pool, 16 tiles. So let's go through and graph this. The first thing that I'm going to do here is my first point. So you can see they've got 1 foot gives me 8 tiles. So I'm going to come over to my graph and go 1 foot gives me 8 tiles. They then said 2 feet gives me 12 tiles. So I'm going to go 2 feet, 12 tiles. 3 feet is 16 tiles. Something I notice here is that we get a line created for us so that I can predict based right off this line that if I had 4 feet of my pool, I would probably have 20 tiles in it. If I had 5 feet of my pool, I'd probably have 24 tiles in it. And we can keep going up through that pattern. Okay. Something I do want us to take note of here. Let me change my pen so we can see different colors. Okay. For every one side of the pool, for every foot added on, my change is just a 1. But for every foot that I add on, how many feet go up on the pool? 4. So again, that's 4 feet. So we can, here is 4, here is 4, and here is 4. Okay, whereas going this way is 1, 1, 1, and 1. Okay. And you guys probably don't remember this. I'm going to go with saying probably not. But this gives us the equation of y equals 4x plus 4, which is essentially the same as our equation of saying our total tiles equals 4 times the side plus 4 additional tiles. Okay. Let's go on to question 7. So just looking at this function, this equation right here, they want to know what is the domain and what is the range of just this function, just this equation. When they say mathematical function, they are referring to that fancy equation right there. Okay, and so with this, the basic answer of this is that every real number makes sense as an actual input, okay? So with this, every number makes sense as an input. So our domain, meaning we can plug in 0, we can plug in 500 for x, we could even plug in negative numbers. Not looking at this problem, just looking at this equation. For x, so for our domain, as a reminder, are our x values, we're going to say all real numbers. Okay? Now my range, that's my y values. Again, just looking at this equation only, my range can also be a number. If I plug in a negative to this, negative 1 times 4 is negative 4 plus 4. That's 0. If I plug negative 2, I could get a negative answer all over. So again, we're going to call this all real numbers. It can be anything because it doesn't matter what we plug in. However, we have some restrictions on this particular problem. So we're going to go down here and look at part B. They want to know specifically for Anthony's pool tiling problem. Okay, this is a discrete situation, meaning this is not a line. It is just data points. Remember, continuous means a line. Again, we did not draw a line. We drew a dash to show the relationship, but these were just points. So this is discrete, not continuous. Okay, meaning it can't be every single value like we set up here. So when it wants to know what is the domain, the important thing to remember here, again, x values, is that in this problem, Anthony only worked with whole tiles. He didn't work with half tiles. He only did whole feet. So with that, we're going to say, and again, we're going to say that the domain, we're going to say the domain is going to be 1, it can be 2, it can be 3, it can go on and on and on for the number n, which needs to be a positive integer, a positive number. Okay, and this n stands for any number. But we can't say all real numbers like up here because this includes halves. Okay, and it also includes negatives. This does not include negatives. Okay, so now let's talk about the range. My range is going to be my y values. Okay, again, this one's going to be a little bit different. Before we said that it could be all numbers. Well, in this case, it can't. What is the first number that it starts at? It starts at the number 8. So my first number is going to be 8. My next number is 12. And then 16. And then again, this can go on and on and on for not just any number, but for the pattern of 4 times any number plus 4. Okay? Again, where that n is positive. That's a tough question there, guys. Okay? So let's go ahead and turn your page to question 8. Okay, so now Anthony's getting a little full of himself here. And he comes up with a different pattern. Instead of just the plain pattern that he had before, he decided, hey, let's add an additional 4 tiles. Okay, so we're going to come up with something to represent his new pattern. And something I want to talk about here, as a reminder, numerical. A numerical representation means a table. Okay, so with that, I'm going to say, in my table, we have the length of the side and the total tiles. Okay, so let's say we're going to go 1, 2, and 3. Well, let's start with what we have here. We know that when his length is 3, like they show us in the picture, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Without the original, there was 16 total tiles. I know this because we've done this problem over and over again. 16 total tiles. But if he does his new pattern, that's adding 4 more tiles on, which gives us a total of 20. 20 tiles. Okay, so if we go down, and I'm gonna draw a picture so you can see it here. If here's a 1-foot pool, and we had our standard pattern, so the 4 sides plus the 4 corners. So now we're sitting at 3, 6, 8, and then our new fancy one, 9, 10, 11, 12. So if we've got 1 tile, that's going to be 12. If we had 2 tiles, I'm not going to draw the pattern out again, but if we had 2 tiles, I know based on my original problem, we would say 2 times 4 sides to get 8, plus my 4 corners would be 12. And then an additional 4 corners, we're going to add another 4 to it to get 16. Okay. So now what I'm going to do is we're going to create a verbal representation. Okay. Meaning words. And all you need to do when we talk about the words is you're going to say, hey, this is the change that happened. So when I go back up here, the first thing I'm going to look at is my sides. My sides are all increasing by a +1. Okay, so tell me then, what are my tiles doing? From 12 to 16, it's plus 4. From 16 to 20, it's plus 4. So verbally, what I would say there, when the pool side is increased by 1 foot, the total tiles increases by 4. So again, this is, you're just telling me the change that happened. Okay, let's check these. We're good so far. So now let's go on to part C. Part C is the graphical representation here. So I still have my tiles here for me to see. That makes it nice and easy. First thing that we're going to do is we are going to label this graph. We're going to call this our length in feet. And over here, this is going to be number of tiles. Okay. I'm going to make this graph a little smaller. We do not need all of this space. In fact, I'm going to make this a 1, 2, 3, 4, 5, 6. Number of tiles, we're going to call this 5, 10, 15, and 20. Okay, so we may be off a little bit here. It looks like I'm off a little on my graph there. So based on this table over here, we know that when he had 1 length of pool feet, there was 12 total tiles. So 1 pool feet, I'm going to go up to about here on my tiles. When there was 2 feet of the pool, I had about 16 tiles. And when there was 3 feet of pool, I had 20 tiles. Okay, and let's see if we match that. Yep. Okay, and if it helps, guys, go ahead and draw. Again, this is discrete because they're just points, but we can put a dotted line, a dashed line, to help us see the pattern that's happening there. Okay, so I want us to come over here again and look at our table that we made. Okay, we said 1, 2, 3, 12, 16, 20. Okay. Our original equation, the OG, guys, the original equation, we said the total tiles equaled 4 times the side plus our 4 corners. Okay. What was different about this one? We didn't just have 4 corners. We had an additional 4 corners. Okay. So we're going to take our original equation, T equals 4 times the number of sides plus the 4 corners plus our new 4 corners. And we're going to simplify this down to get our total number of tiles equals 4 times the side, the length of the side, plus 8 sets of corner tiles. Okay, so with that, guys, we should be done. Numbers 9 through 12, along with number 5, are homework. So again, number 5 and then 9 through 12 are your homework. Okay, we'll be back in class here to answer any questions and to work on some of this. Bye.